We will wait for a couple more minutes. Just 2 minutes more and then I will start, okay? So good afternoon everyone, myself Anjali Negi. So a little bit of introduction. So I am currently a PhD student in IIT Kanpur. So I am pursuing my PhD in physical chemistry. Okay. So today I will start with statistical mechanics, some basic of canonical ensemble. So there were 2 questions, so I will share one by one. Okay. Chemistry. So hello everyone. In this video, I will be solving GATE 2017 question number 1, chemistry. So this question states that consider n particle at temperature T, pressure P, volume V, and chemical potential mu having energy E. The parameters that are kept constant for a canonical ensemble are. So we have to define the canonical ensemble. So before jumping into that, let's just find out the basic. So what are ensembles? So ensemble, we consider that they are the mentally a large number, consider mentally a large number of systems which have the same macroscopic property like number of particle n, volume v, energy E, or temperature if energy is allowed to vary. Such a virtual mentally constructed replica or collection of thermodynamically identical system is called an ensemble. or a statistical ensemble. Now, if we look into this figure, this is actually the super ensemble of micro ensemble. Sorry, micro canonical ensemble. Here, what we have done, so it is actually a representation of canonical ensemble where energy of each system can fluctuate. The system is kept at a fixed temperature T by this system is actually kept at a fixed temperature T by putting the super system in a bath and establishing a thermal contact between the individual system. So each system, these small boxes are at a fixed temperature, capital are at a fixed temperature, capital
Just wait, I will reload it.
ensemble, and which are actually made up of small super ensemble of micro canonical ensemble. Again, I can write it as an ensemble with a constant number of particles n in a constant volume V and at thermal equilibrium with a heat path at constant temperature capital T can be considered as an ensemble of microcanonical sub-ensemble, as I have discussed here, with different energies EI. Okay, so such an ensemble is called a canonical ensemble. Correct? So the correct answer for this, that the parameter that are kept constant for a canonical ensemble are number of particle, volume, and the temperature, and VT. So A is the correct option. So I will highly recommend you to go through the book Statistical Mechanics for Chemistry and Material Science by Professor Biman Bakshi. You can also go and check this reference for the NPTEL Canonical Ensemble Part 1 by Professor Biman Bakshi, Department of Chemistry, IIT Bombay and IISc Bangalore. So here is the link attached. Thank you.
Yeah, any of you have doubts?
Clear, ma'am.
Okay. So, just a quick question, like, so the microcanonical ensemble. So, what are the parameters for that?
NVE.
Yeah, correct. And this canonical ensemble is actually generated from the microcanonical ensemble itself. So, actually, the microcanonical ensemble, the parameter are NVE, but when we do experiments, we generally take pressure or temperature as a parameter to vary, correct? So the role of energy is very crucial here. To keep it constant is actually very it's not very practical. So that's why we what we do is we the microcanonical ensemble is the mother of every other ensemble, because we take that and then we isolate the whole system and make it constant with some parameter which are actually practical possible. So that's how I have just to show you again the picture here. So here that is what I was saying. I don't know whether it was very clear or not, but it was, this system, whole system is a isolated one, kept at a temperature T, and these small boxes are actually representation of the micro canonical ensemble, which itself is an ensemble of energy E7, for example, and that is why the energy E7 is constant for this particular box. But when we take the whole ensemble of microcanonical ensemble and keep them together, and they can exchange the energy with themselves, so we make a super ensemble, which is called as a canonical ensemble. Okay, so I will share the another video also that is also similar to this, but it contains the partition function also. Okay.
Hello everyone. In this video, I will be solving GATE 2018 Chemistry question number 46. This question states that at the temperature T, the canonical partition function of a harmonic oscillator is with fundamental frequency mu is given by. So this is the expression for the canonical partition function of a harmonic oscillator. So we have to find the probability of the harmonic oscillator in the ground state, given h mu by kBt is equal to 3. So before solving this question, let's have some basic here. So when we talk about the canonical partition function, it is the ensemble of a microstate So when we talk about the canonical ensemble, so when we talk about the canonical ensemble, it is the ensemble with a constant number of particle n, okay, and a constant volume v, and they are at a thermal equilibrium, that is T, correct? And they can be actually considered as an ensemble of microcanonical subensemble. So like this small box can be considered as a sub-ensemble of microcanonical. Okay. So these among these microcanonical ensemble, we have a different. Okay. So these among this micro canonical ensemble, we have a difference in energy. Okay. But as a super ensemble, which I am calling it as canonical ensemble. Okay. So under this particular sub-ensemble of micro-canonical ensemble is actually having a constant energy E7. Okay, but among each other they can exchange the energy. So this is what we call a super ensemble, and so this is isolated. Okay, and having a temperature T. Now, so this is actually the representation of canonical ensemble. So here the energy of each system can fluctuate. The system are however kept in a fixed temperature T by putting the super system in a bath, and we establish a thermal contact between the individual system. So each system is actually at a constant NVT. Okay. Now, so here, if we look into the energy distribution, so this is the distribution of particle in a canonical ensemble having a set of energy value from say E6 to, from say E6 to E10. Okay, so we are going from E6 to 10 as here shown in the figure. So the arrow indicate the particles and the horizontal line are energy levels here. So you can see that in the distribution in energy is equal to 10 is actually we get only two different distribution, and for energy equal to 8 we get four different distribution, and similarly we get for energy 6 equal to 6 is we get 1 2 3 5 different distribution. Okay. So it is vital to note that all the microscopic state with the same energy are equally likely. So the microscopic state 1, 2 are equally likely with the same energy, and all the four arguments with E equal to 8, that is here, are equally likely, or in E equal to 10, the two different arrangements are equally likely. So, however, the state with the different energies have different probability, and they contribute differently to the overall observed macroscopic property of the system. So, here it is important to find out the probability of a state with a given energy. So now you know why it is very important to find out the probability of each state with a different energy, because they all contribute differently to the overall observed macro state property of the system. So what is the probability of the jth state Pj that being occupied is actually written as Pj equal to small nj asterisk upon capital N, where small nj asterisk is the desired most probable distribution of the jth state, and capital N is the total number of NV system in the ensemble. So we can actually write it as E to the power beta, uh, uh, where my beta is equal to 1 upon kBt. Okay, and Ej is the energy, and here in denominator you get the sum over all the states, that j states, and we get the exponential to the power beta Ej, energy Ej. Okay, So the term in the denominator is actually termed as the canonical partition function, Q, with constant NVT parameter, and the thermodynamic quantities like free energy, entropy, etc. can all be obtained from Q. So these relations form an important part of statistical thermodynamics. Now, okay, to solve our problem, we know that my probability, we have to find out for the ground state. So my probability for ground state, that is J is equal to 0, will be P0 is equal to N0 upon capital N, which will be written as the exponential E minus E0 upon KBT and upon the canonical partition function for the given. We are given with the ground state, harmonic oscillator. So this expression will be E minus E0 upon KBT upon e to the power minus h mu upon 2 KBT 1 minus e to the power minus h mu upon 2 KBT. Correct? Also, this energy expression E0, so we have to write the energy expression E0. For our harmonic oscillator, the energy expression is given as mu plus 1 by 2 h cut mu, where this is my vibrational quantum number. So this goes from 0, 1, 2, etc. So for E0, it will be 1 by 2 h cut mu, or we can write it as h mu, right? So this expression becomes P0 is equal to e to the power minus h mu upon here it will be 2 by 2 KBT upon e to the power minus h mu upon 2 KBT, and this expression comes up and we can get E1 minus e to the power, and I can actually write it as minus h mu upon 2 KBT. So this cancels out and my expression again becomes, so 1 minus e to the power minus h mu upon 2 KBT. Okay, and we are given that this particular part is equal to 3. So my expression becomes 1 minus e to the power, a minus sign, and 3. So when I solve this, my probability is equal to 0.95. So we have to write the probability of finding the harmonic oscillator in the ground state is 0.95. Again, I will recommend you to go through the book Statistical Mechanics for Chemistry and Material Science by Professor Biman Bakshi, and the particular lecture Canonical Ensemble Part 1 by Professor Biman Bakshi, and Part 2 also. So Department of Chemistry, IIT Bombay and IISc Bangalore. So this is the link attached here. Thank you.
Yeah, any of you have any doubts? Also,
Clear, ma'am.
okay. Also, any doubt from previous lecture that I have, previous question that I have taught or solved, because I only have one video left and that will be the last one. Okay, I will. What is it? I'll share the screen now.
Hello everyone. In this video, I will be solving GATE 2018 Chemistry question number 48. This question states that in a molecule XY, let psi x and psi y denote the normalized atomic orbital of atoms x and y respectively. A normalized molecular orbital of xy is given by this expression. The value of the overlap integral of psi x and psi y is. So, before solving for this expression, let's get familiar with what are the atomic and what are the molecular orbitals. So we are given atomic orbitals. So to
Yeah, I will again share the screen because that was not having the good quality.
question number 48. This question states that in a molecule XY, let psi x and psi y denote the normalized atomic orbital of atoms x and y respectively. A normalized molecular orbital of xy is given by this expression. The value of the overlap integral of psi x and psi y is. So, before solving for this expression, let's get familiar with what are the atomic and what are the molecular orbitals. So we are given atomic orbitals. So we are given the atomic orbitals of our molecule X and Y, and psi X and psi Y are respectively the atomic orbital of X and Y atoms. So the molecular orbital is a linear combination of atomic orbital. So we can actually call it as LCAO molecular orbital. So the linear combination of atomic orbital can be written as psi plus minus C1 psi x plus minus C2 psi x. Now this is a general expression. Here this psi plus is my bonding molecular orbital, and this bonding molecular orbital is written as C psi x plus psi y. To find the normalization expression for this psi plus, we have to put psi plus in the normalization condition. So the expression for normalization is the integral over whole volume space. So psi x conjugate is multiplied with psi x, or actually I can write it here as psi plus conjugate with psi plus equal to 1. So when I put psi plus expression into this, I will get c square integral dr. So psi x conjugate plus psi y conjugate multiplied with psi x plus psi y equal to 1. Now when we solve this, we get 4 different integral. So here this 4 different integral get further simplified when we apply the normalization condition. So again this first integral and this third integral are equal to 1 because of the normalization condition, and this second and the last expression is equal to s. This s is actually the overlap integral, capital S, which is the overlap between the two atomic orbitals, so that is x and y. So we
Actually, there is a mistake. I am saying here that the first and the third expression is actually normalization expression, but the correction here is that the first xx and the last one is equal to 1 because of the normalization condition is fulfilled. So here is the correction. Okay.
we can so this expression psi x conjugate psi y and psi y conjugate psi x is equal to capital S. So we get c square 1 plus s plus s plus 1. C square is common. So on solving this, we get c is equal to 1 upon under the root 2 multiplied with bracket 1 plus capital S. So here we know that our normalized expression for, so this is my normalized molecular orbital. So actually this is a bonding molecular orbital. So my normalized bonding molecular orbital will be psi plus equal to, where this was earlier C. So I have replaced the expression for C with 1 upon under the root 2 into 1 plus S. So this is my overlap integral. So S is, so yeah. So we have to find S here. So in our question, we have to find, we are given with the expression psi plus is equal to 0.56 multiplied by psi x plus psi y. So when we compare these two expressions, we know that 0.56 is equal to 1 upon under the root 2 1 plus s. Here we have to find the overlap integral, and overlap integral is capital S. So we have to find S here. So this will be, after solving, S equal to 0.59. So the answer for this is, the value of the overlap integral is 0.59. I will highly recommend you to go through the lecture number 61, Molecular Orbital Theory for H2 plus ion. This given by Professor Anindya Datta, Department of Chemistry, IIT Bombay. This is the link. Thank you.
Okay, any doubt in the last question?
Clear, ma'am.
Okay. Just tell me that the overall overlap integral that we were talking about is, I mean, what do you understand by it, and what at what parameter it depends on? You can give your answer in the chat box too. Can you guys see the whiteboard?
No, ma'am.
Okay. Yeah, now can you see?
Yes, ma'am.
Okay. So the overlap integral that I am talking about is just simply understand that, for example, I don't know how it works. For example, consider one atom here and the other here. Okay. So this is for, say, it's A, B. So the when we talk about overlap, so we say that the wave function or the atomic orbital and the atomic orbital of A and atomic orbital of B actually overlap, and for, we were talking about the bonding molecular orbital psi plus. So in that condition we actually get a sigma type orbital, and maximum electron density is at the middle of the two atoms, correct? So this is something like this. And so this is the overlap integral. Also the parameter that I am talking about, I should actually check. Okay, none of you have typed the answer, so yeah. So the parameter that I was talking about is the capital R, that is the nuclear distance, the distance between atom A and atom B. So at that parameter, my S, my overlap integral, is directly proportional. So it doesn't, it has a expression S depending upon R, has a expression. You can check it in the Macquarie book, quantum chemistry book, or Levine. So yeah, so it has a direct dependence on the distance between two nucleus of the atom A and B. Also for psi negative, that is the anti-bonding molecular orbital, we will be having the electron density what, minimum or maximum at the middle? For anti-bonding it should be minimum. So that is why there is a node, okay, node formation. So you can very systematically it is demonstrated in the books. You can go after this lecture, you can check that out. So any other doubts? So Mathi Mani, I have not I am seeing you for the first time attending my live. So what are you doing? You are a student? No, I couldn't hear you. I think you can type because I cannot hear you. Also, yeah, as the distance between the two atomic or nuclear atom A and atom B increases, that is the R increases, the overlap will also decrease. Okay. Okay. So any other feedback or suggestion you want to give? All of you. Yeah, Mathimani, you completed your MSc. Okay. So the lecture actually I am making, the video lectures, is it clear to you? The message comes to you, or you don't understand?
It's clear, ma'am. It's understandable.
Okay. So none of you have any feedback? So Mathi, from where you have completed your MSc? Oh, nice, Trichy. Okay. Okay, so yeah, someone was saying
Ma'am,
something.
that overlap integral S,
Mm-hmm.
it has relation with the distance R as E as I'm seeing it from the book is E raised to power minus R upon A naught. R we got is the distance between the two nucleus. The A naught is the Bohr distance, or could you explain the A naught?
Yeah, wait. Actually, I have also you are looking at Macquarie. Yeah, I also have opened the Macquarie right here. The expression 9.11, the expression with e to the raised to the power minus r, right? But it doesn't have the a naught.
Doesn't have A naught. Okay, ma'am.
I mean, because I am looking at the book.
Okay, ma'am.
Yeah, the whole expression is actually I cannot share the screen. This Google Meet is not able to share this. Yeah, actually it can able, but only the video is not there. So I can share. wait. Okay, I'm not able to share, but yeah, you can check the expression. It only has capital R in that whole expression. Okay.
Okay, ma'am.
Also, lastly, I will just ask you that what is the difference between CCP and HCP packing? Yeah, anyone?
Ma'am, CCP and
HCP. So we generally, I have generally seen that people take HCP and CCP very similar, but they are very similar, but there is a bit difference between them. So one is the, I'll just write it here. One is the CCP, that is cubical close packing, and another one is the HCP, that is hexagonal close packing. So what is the difference? Yeah, Mathi, Gunasli, you can type your answer in the chat box. Okay, so the difference is okay. So in hexagonal, the pattern of the packing is only the difference between the two. So one will have A, B, A, this kind of packing, and the other one will have A, B, C. So you guys understand what is A, B, A and A, B, C? So I'm just seeing that same number of people attend this live session. So if you guys are okay, then I will just add one tutorial of this clearing some solid state basics. Ashish, you are not audible. You can type.
yes, ma'am. Clear, ma'am. Clear, ma'am. I said clear.
Okay, it's clear, but I'm asking whether I should add the tutorial in the next live.
Yes, ma'am.
Okay. Okay, I will add the tutorial. Other two, you are not responding. I don't know why. Whether you have just leave the meeting or. Okay, last question. Just it just in my mind that the octahedral voids and the tetrahedral voids, correct? They form in a close packing when we do the close packing and all. So the octahedral void, where does it? Where is the formation of the octahedral void in our cube? So the octahedral void, where does it form? Like so if I'm so if I create this cube, just imagine it's a cube. So my question is that in CCP packing, phase center packing, HCP, for example, my atom occupy the corners. Okay, so here are my atoms occupying all the corners. Okay, so I'm just asking that if it's a CCP packing, I'm not drawing all the atoms, but where will be the formation of the octahedral voids? Okay, so I will discuss these in detail in the next. If you are interested, I will add the tutorial at the end of the videos. So yes, so actually this octahedral void is present at the first of all at this edge center. So at each edge center my one octahedral is formed, octahedral void is formed. Okay, and another also I think along the body diagonal, or I have to check that, but it's something like that. So that is also we get the why my octahedral voids are more than the tetrahedral voids. So I will clear all this concept in the next. So okay. Okay, you guys can log out now. Thank you so much for attending.
Thank you, ma'am.
Thank you.